Hello, welcome to the second lecture of infrared spectroscopy. In the first lecture, we had a discussion on the vibrational spectra of simple harmonic oscillator. They are having the same frequency of absorption at different energy levels. But real molecules do not obey the laws of simple harmonic oscillator model, since the bonds are not homogeneous as by Hooke's law. If the bond between atoms is stretched, there comes a point at which it breaks and the molecule gets dissociated. That is, at lower energy levels, the bond may be taken as perfectly elastic, but at higher energies, the system becomes complicated. Thus, the energy level diagram for a typical diatomic molecule will be different from that of an ideal case. For the ideal molecule, it will be perfectly elastic even at higher energy level, but it is practically impossible. Hence, we need a new energy expression to represent the transition in real molecules. For this, P.M. Morse derived an expression of energy to fit in this curve called Morse potential or Morse function, which is expressed as E equal to dE into 1 minus e raised to a into Req minus r the whole square, where dE is the dissociation energy of the molecule that you can see in this figure. That is, it is the distance between the low energy level to the dissociation limit. R is the internuclear distance and Req is the equilibrium internuclear distance, and A is an empirical constant characteristic of the molecule. When this equation is used in Schrödinger equation, the new allowed vibrational energy levels will be given as epsilon V equal to V plus half into mu bar minus V plus half the whole square mu bar E into chi E. Here I am giving the vibrational frequency mu bar as mu bar E because it is the equilibrium, at the vibration frequency at the equilibrium position. And the new factor is chi E, which is known as the unharmonicity constant. And it is a small positive value of 0.01. If this unharmonicity constant chi equal to 0, the energy expression will be the same as in the case of a simple harmonic oscillator. Thus, this equation can give the the spectra of this equation can give the spectra of a unharmonic, the energy level of unharmonic oscillator, and the energy level transition will lead to the spectra of real molecules. Then Due to the second term, anharmonicity term, the energy level becomes closely spaced, especially at higher range, higher energy levels. This is because the chi-e is a small positive value and we have take a difference from the second factor to the harmonic oscillator, and it gives an unequal distribution of energy level. Thus the Morse curve for the diatomic anharmonic oscillator will be like this, having a dissociation energy from equilibrium position to the dissociation limit. It will show a dissociation limit, not extend to any level. For the anharmonic oscillator, there is also a selection rule, but it has changed from the harmonic model that it can have the values plus or minus 1, plus or minus 2, plus or minus 3, etc. That is, for an anharmonic oscillator, there is a chance for larger jumps. There is an additional possibility of larger jumps. But usually at room temperature, most of the molecules are in the ground vibrational state, so that the most probable transitions are from the zero vibrational level to the higher states. And for the transition from 0 to 1 state, ground state to the first excited state, the delta V is equal to plus 1, and the change in the energy E1 minus E0 will be getting from the anharmonic energy level expression. That is, if we are putting V in place of 1 in place of V, we will get the expression like this, and when calculating we will get nu E bar into 1 minus 2 chi E centimeter inverse. The next, this transition is having much probability that it's possible to get excited to the first level is the more probable type of transition. And for the transition from ground state to second level, we will have 2 in place of 1, and the same calculation gives the new vibrational frequency nu 2 nu bar E into 1 minus 3 chi E centimeter inverse, and for the other transition we get 3 nu bar E into 1 minus 4 chi E centimeter inverse. Also, since this chi E is a very small positive value, the 3 spectral lines will lie very close to, the first spectral line will lie very close to the fundamental frequency nu E bar, next will be close to 2 nu E bar, and the next will be close to the 3 nu E bar. The first line, which is known as the fundamental absorption band or fundamental absorption line of the spectra, as it is, as I have already said, it is the most probable transition. And the other less intense transitions are called overtones, and the first delta V plus, the transition due to delta V plus 2 is the first overtone, next is the second overtone, third overtone, etc. Next, along with this, I have to mention one more term which is known as Horde bands. You can get an idea of the concept by its name itself. That is, if we are recording the spectrum at higher temperature, the samples will be at higher temperature, the population of the first energy level will become appreciable. As the molecules in the ground state get enough energy to excite, there will be an appreciable population in the first state, and then weak absorptions may arise from the first level to higher states. And for V equal to 1 to 2, we will get an absorption line by the previous calculation as nu E bar into 1 minus 4 chi E centimeter inverse. And here also you can see it will be very close to the fundamental absorption band as chi is very small. And if we are recording the spectrum at different temperatures, we will get new lines close to the fundamental absorption line, but with a very low intensity. The 350 Kelvin temperature band is just appearing the line, since at the molecule may be in the 5th or 6th level initially at this temperature, and there's a chance for the population will be lower, so that this spectral line will appear like this. So it is known as Hode bands, as it is recorded in the by increasing the temperature. And thank you, students.